In this video we're going to go over transient heating and cooling. So it's regulated by this equation here. We have the temperature in Kelvin of the fluids, initial and final, to the exponential of negative time over this symbol, which is tau, the Greek letter. And tau is a time constant. It can be calculated using these equations, which we'll use later in an example. So to use the equations above, we assume the system has a very high thermal conductivity. So the temperature throughout the solid is uniform. To justify if the assumption is reasonable for the system, we use lump system analysis using the BO number, which is the BI number here. And it has to be less than 0.1 to be accurate within 5%. So if we apply it to an example here, an aluminium cylinder, length 7 and diameter 2, we'll assume these are meters, is initially at a temperature of 350 degrees Celsius and is plunged into the water at 30 degrees. So if we start labeling the values that we have, and loses heat with a convection heat transfer coefficient of 100. The thermal conductivity of the cylinder is this. Specific heat capacity and the density. Let me just check that all of these are in the SI units as well. So how long will it take for the temperature of the cylinder to drop to 65 degrees? So because if you look on the left hand side of this equation here, we have temperature minus temperature, temperature minus temperature, and they're divided. This side is going to be dimensionless, which also tells you that this side would be dimensionless as well. So it doesn't matter if we're in Celsius or Kelvin, because they're both being minus, so the difference will still be the same. So if we plug that into our equation, we have 30 minus 65 divided by 30 over 350 equals e to the negative t over tau. So we need to calculate tau because it wants the time, how long will it take for the temperature. So it wants the time in seconds. So to work out tau, we use the equations above. The one we're going to use is this one. So if we plug in our values, we have 2702 multiplied by 903 multiplied by, now LS, as shown here, is the volume divided by the surface area for heat transfer. So we are going to assume that the surface area for heat transfer is just the circular side, not on either of the ends, because they're smaller in comparison. So for LS, or characteristic length, it's volume over surface area for heat transfer. So the volume of a cylinder is pi r squared. The radius is 1, multiplied by 7 because of the length, divided by the surface area, which is pi d, so 2 pi multiplied by 7. So if we put that into the calculator, or we can just cancel, we get a half. So we can put our characteristic length into our equation, and we're given the overall heat transfer coefficient. So our value of the time constant tau comes out to 125.643. So now we can rearrange to find T. So on the left hand side, if we minus and divide everything by everything, we get 7/64 equals e to the minus t over tau, which we've already calculated. If we take the natural logarithm of both sides, we can get rid of this exponential. So we have ln 7/64 equals negative t over tau. Then if we multiply both sides by -1 and both sides by tau, we can get t by itself. So negative ln 7/64 multiplied by tau, which when we put into the calculator gives us 278.0 seconds. If we wanted it in minutes, that's 4.6 minutes for the temperature of the cylinder to drop to 65 degrees. And that's it.